Students, in this note set, we're going to take a look at the shapes of molecules, which result from writing good Lewis structures for them. First of all, we know that an atom's ability to bond depends on its valence electrons and how they're arranged. But if we take that a step further, and we say, okay, we know something about atoms. We know something about how they can bond together following the octet rule with some various exceptions to that. But what if we have a collection of molecules, what you might call a substance? The properties of that are dependent on the shape of the molecule. And the shape of the molecule determines how collections of molecules interact with each other. We can predict molecular shapes from good Lewis structures. So all of the work that you've been doing in this unit is leading us up to this point. Okay, let's go back a little bit to some basics. In science, opposite charges attract. So a positive charge is going to attract a negative charge. Similar charges repel. So a positive charge will repel another positive charge, and a negative charge will repel another negative charge. When we're writing Lewis structures, and when we're considering chemical bonding, it's all about the electrons. Yes, an atom has both a positive nucleus and negatively charged electrons surrounding the nucleus in various places called orbitals, which we've studied. But when a bond is formed, the first thing that comes closest from one atom to the next are the electrons. So when we think about molecular shape, we really need to think about how electrons are going to repel each other. Any two electrons in an atom will have the same kind of charge, a negative charge. Electrons, after all, are negatively charged subatomic particles. They're going to repel each other. So all of our work with molecular shape that we're about to take a look at is based on this principle. Electrons repel each other. They want to get as far apart from each other as they possibly can. There's a theory that explains molecular shape. It's known as VSEPR theory. Now, everybody in chemistry pronounces that Vesper, so don't be surprised if you hear Vesper, and it really is VSEPR theory. Here's the idea. If we know the Lewis structure, we can predict a molecule's three-dimensional shape. The V in Vesper stands for valence, the S stands for shell, E for electron, P for pair, R for repulsion, and then theory is there. So if you put that together, valence, shell, electron pair, repulsion theory, it means when we're considering the valence electrons as shown in Lewis structures, which always act in pairs, always, except for substances called free radicals, which we're not going to touch in this class. They're repelling each other. So here's the gist of Vesper theory. A molecule's shape can be found by minimizing repulsions among the electron groups that surround the central atom. We're going to be focusing almost exclusively on the central atom in a molecule. Okay, I used the term electron group. What's an electron group? All right, this is important, students. Any one of the following counts as an electron group. A lone pair of electrons, that is, a pair of electrons that's not bonding. It belongs entirely to the atom that possesses it. It's the dots in the Lewis structure. A single bond, that counts as an electron group. A double bond, that counts as one electron group. A triple bond, that counts as one electron group. Now you might think, why can't a double bond count for 2? Well, it's still a group of electrons doing a task. In the case of a double bond, it's bonding with another atom in the molecule. And then another question that often comes up is there such a thing as a quadruple bond? No, there is no such thing. Quadruple bonds don't exist because the atoms that are participating in that form of bonding would have to twist around each other in such a way that's not possible. Okay, let's take a look at a few molecules and just count electron groups. That's all we're trying to do here. Here's carbon dioxide, CO2. We're focusing on the central atom, so just look at the carbon. Don't worry about the oxygens. Around that central carbon, I see a double bond to the left and a double bond to the right. That's all I see. There are no other dots around the central carbon. So if there's 2 double bonds, that means there's altogether 2 electron groups around that central carbon atom. Let's try another one. Here's water. We're focusing only on the central oxygen. We don't care about the hydrogens right now, just the central oxygen. Around the central oxygen, I see a single bond to the hydrogen on the right side, another single bond to the hydrogen on the left side, a lone pair of electrons above the oxygen, and a lone pair of electrons below the oxygen. Every one of those counts as 1 electron group. A single bond counts as 1 electron group. A lone pair of electrons counts as 1 electron group. So altogether we have 4 electron groups around the central oxygen atom. 2 single bonds and 2 lone pairs. Let's try another. Ooh, look at this. Ammonia, NH3. We're only focusing on the central nitrogen. We don't care about the hydrogens right now. Around that central nitrogen, I see 1 single bond here, 1 single bond here, 1 single bond here, and a lone pair of electrons. Altogether, that's 4 electron groups around the central nitrogen atom, 3 single bonds and 1 lone pair. Students, if you can do that counting, you're 90% of the way there for figuring out molecular shape. And here's other good news. As far as determining molecular shape is concerned, I'm going to be providing the Lewis structures, except for one comprehensive question at the end of this note set. I'm going to assume that you can do the Lewis structures in order to be able to determine molecular shape. Okay. There are 4 steps that we're going to follow when determining molecular shapes. Number 1, start with a good Lewis structure. If you didn't do a good job writing a good Lewis structure, nothing else matters. You're going to get everything else wrong in terms of finding molecular shape. You've got to have a good Lewis structure to begin with. Second, we're going to count electron groups around the central atom, just like we did on the previous slide. Counting electron groups is as simple as finding which atom is central and then counting 1 for every type of bond, whether it's single, double, or triple, counts as 1. If it's a lone pair of electrons, that counts as 1 as well. Third, and here's where it gets a little interesting, we're going to place electron groups as far apart as possible in 3-dimensional space. Remember, electrons repel each other. They want to get as far apart as possible. That placement of electron groups as far apart as possible is what determines what we call the electron geometry of the molecule. And then fourth, final step here, look at how the electrons are actually shared in the Lewis structure. In other words, the electron geometry is based on electron groups, which might be bonding pairs or it might be lone pairs. But when we determine molecular shape, we're only considering bonding pairs. The positions of the actual atoms in the molecule are what determine molecular shape. As we continue in this note set, I think that distinction will become more clear. Okay, let's consider a little analogy. Let's say I've got balloons and they're tied together and they're just normal round balloons. I'm not looking at the long skinny balloons, just normal round balloons. When balloons are tied together, they behave in such a way that they move apart. They're trying to give all the other balloons as much space as possible. So if I take, let's say, two balloons and I tie them together, they're going to come to a resting position where the balloons are pointing exactly opposite each other in space. In other words, if you were to draw a line between the two balloons, the central parts of the two balloons, they would be oriented 180 degrees apart. What if we took three balloons and tied them together? Well, if you tried tying three balloons together, you'd get three balloons pointing as if they're oriented to the vertices of an equilateral triangle. You get bond angles of 120 degrees in that case. Now, thus far we've been thinking in terms of a plane, because 3 points make up a plane. But what if we add a fourth point? Now we need to think in 3 dimensions. When you tie 4 balloons together and try to get them as far apart in space as they can be, you're forming a shape that is a triangular based pyramid. We call that a tetrahedron. When you have 4 balloons, they orient 109.5 degrees apart in 3-dimensional space. How about 5 balloons? Check this one out. Here, you'll get 3 balloons within a plane oriented 120 degrees apart from each other, but you'll also get a balloon pointing above the plane of that triangle and a balloon pointing below the plane of that triangle. The bond angle separation between the balloon pointing up and the balloon pointing down to either of the balloons within the plane of the triangle is only 90 degrees. So there's 2 angles to consider in a 5 balloon arrangement. And then lastly, what if we had 6 balloons? Here, we'd have a shape called an octahedron. An octahedron is a square-based pyramid, like the pyramids in Egypt, but there's 2 of them facing bottom to bottom. And that gives you an 8-faced shape, if you could imagine the shape that results, called an octahedron. Now, why are we talking about balloons? Well, as it turns out, the shapes of these balloons are similar to the shapes that electron groups take in molecules when they repel each other. When you have 2 electron groups in a molecule, the bond angle separation is 180 degrees apart in space. So A here in this picture is the central atom. And if you have 2 electron groups coming away from A or attached to A in some way, and they want to get as far apart from each other as possible, because remember, electrons repel, then you can get 180 degrees separation. We call that linear electron geometry because it looks like a straight line. Okay, what if we have 3 electron groups? This is like having 3 balloons that are trying to repel each other. Here you can get a triangular shaped separation with 120 degree bond angle separations. We call this trigonal, so triangular, and then planar because it's all in a plane, electron geometry. All right. For 2 and 3 electron groups, it's okay to think in just a plane. But when we get to 4 electron groups, now you need to think 3-dimensionally, and this gets a little challenging. Picture a pyramid that has, instead of a square at its base, a triangle at its base. So if you trace the outline of the base of this shape, you get a triangle. And then there's around that 3 faces. Well, it just so happens that that is a 109.5 degree bond angle separation. And the shape that results, so if you can imagine the electron groups pointing to the vertices of this shape, you get what's called a tetrahedron. So we have tetrahedral electron geometry when you have 4 electron groups. Now notice, if you have a central atom following the octet rule that is not double bonded, you're going to get tetrahedral electron geometry. So this is probably the most common of the electron geometries. Here's a way to visualize it. Take methane, CH4. You have a central carbon. You have 4 hydrogens coming out of that central carbon atom. The bond angles achieved are 109.5 degrees in space. Now, it becomes impossible to accurately represent this on a flat screen or a flat sheet of paper. And so we've got to use our imaginations here. Believe it or not, if you were to rotate this molecule, it would look the same from all sides with the same angle, 109.5. Okay, let's see if we can push this a little bit further. All right, what if we have 5 electron groups around the central atom? And I know what you're thinking, this means we're violating the octet rule. Absolutely, yes, you would be violating the octet rule. We know how to violate the octet rule at this point. So you've got to have a central atom that is not in the top 2 rows of the periodic table. So it can happen, and we've seen and written Lewis structures for these kinds of molecules. In this electron geometry, some electron groups achieve a 120 degree separation. Those are the electron groups within the plane of the triangle. Other electron groups are only 90 degrees apart. So if you were to measure the angular separation from any of the groups within the plane of the triangle to an electron group either above the plane or below the plane, you would get a 90 degree separation. So 2 different angles in this type of electron geometry. Now, the name for this is a little bit goofy. First, before I give you the name, I want you to look at the shape. So in the plane of the triangle, you have a triangular base. And then it's as if you have 2 pyramids, one pointing upward from that plane and one pointing downwards from that plane, that are equal. We call that trigonal bipyramidal. That means 2 pyramids, bipyramidal, and with a triangular base. Trigonal bipyramidal electron geometry. It's a funny name. Okay, 6 electron groups. Here, we've got 90 degree bond angle separation, regardless of which 2 electron groups you're comparing. Even the ones above the plane of the square and the ones below the plane of the square. And the shape, okay, take a look at this one. It's a square base pyramid, and there's 2 of them, one of them pointing upwards, one of them pointing downwards. We call this the shape that emerges an octahedron. It's not, it would be cool if it were named square bipyramidal, but it's not. It's called an octahedron. So octahedral electron geometry. I know what you're thinking, students. You're probably thinking, do I have to memorize this? No, I'm going to give you a chart. You can use this chart on any test or quiz, but you do need to visually work through the different shapes so that you know what to apply when at different problems. Let's try this sample problem together. Given Lewis structures for these compounds, count the electron groups around the central atom. Only the central atom. I don't care about the satellite atoms, just the central one. And based on that, identify the electron geometry and the bond angles. So I'm providing the Lewis structures for you, okay? You don't need to worry about picking out new or writing new Lewis structures at this moment. But we're going to take a look at each of these in turn. I invite you to pause the video now to try this problem out and then restart it when you're ready to view the answers. Okay, let's take a look at this one first. Where's the central atom? Carbon. 2 electron groups around it. Each of the double bonds just count as 1 electron group. Whenever you have two electron groups around a central atom, we've got linear electron geometry, and the bond angles that you can achieve in terms of keeping electron groups away from each other is 180 degrees. How about this one? Look at the central atom. We're only concerned about the nitrogen here. Remember, a single bond counts as one electron group, but so does a double bond count only as one electron group. So does a lone pair of electrons. So here we have 3 electron groups. The single bond counts as 1. The double bond counts as 1. And the lone pair of electrons also counts as 1. Whenever you have 3 electron groups around the central atom, we have trigonal planar electron geometry. And the bond angle separations, 120 degrees. Here's a nice one. We have a central carbon, and we're only concerned about the central carbon. Okay, whenever we're asking you in this class for electron geometries or molecular shapes, only consider the central atom. Well, this one's kind of straightforward. You only have 4 single bonds. There's no lone pairs to worry about. Whenever you have 4 electron groups around the central atom, we're talking about tetrahedral electron geometry. And as you may recall, that gives us 109.5 degree bond angle separations. 2 more. Look at this fella. How many bonds are around that central phosphorus atom? I'm counting 5. There's no lone pairs, just 5 straight up single bonds. And when we have 5 electron groups around the central atom, that was trigonal bipyramidal electron geometry. Now, the bond angles, this is interesting. 2 different angles can be achieved with trig bipyramidal electron geometry. Both 120 degrees for the bonds within the plane of the triangle, and 90 degrees if you compare any of the bonds within the plane of the triangle to the bond either above or below it. And then lastly, check this one. How many electron groups are there? I'm counting 1, 2, 3, 4 single bonds plus lone pairs, 2 lone pairs. Yikes, that's 6 electron groups around the central iodine atom. Every one of those counts as 1 electron group. That gives us octahedral electron geometry with bond angles of 90 degrees. Oofta, that's a lot, right? Okay, one important thing. Electron geometry does not always mean the same thing as molecular shape. Geometry of electrons can be different from molecular shape. The electron geometry is based on all of the electron groups, whether or not they're bonding groups. Molecular shape, however, is only determined by the bonding groups. So you've got to subtract out the lone pairs when you're naming molecular shape, because there can be a difference. Let's take a look at a couple of examples. First, take a look at this one, ammonia. If I'm looking at the central nitrogen, right off the bat, I'd say, okay, here's a single bond, here's another single bond, here's a third single bond, plus there's a lone pair of electrons. So there's 4 electron groups around the central atom. That would give us tetrahedral electron geometry. Here's a sketch of that. Notice 3 of the 4 electron groups are bonding electron groups, but 1 of the 4 is a lone pair, a non-bonding group. Now, mentally subtract out the lone pair of electrons, and what do you get? Ah, look at this. It's a molecule that has 3 atoms coming out of it, and they're all oriented slightly downwards, maintaining a roughly 109.5 degree bond angle separation. Okay, so we've got tetrahedral electron geometry. 1 of the 4 electron groups does not participate in bonding, and we name the molecular shape for the atoms that are actually there. So if you mentally subtract out that lone pair, what do you got? What do you have behind? A triangular-based pyramid. Huh. So we call the electron geometry for ammonia tetrahedral. We call the molecular shape or molecular structure trigonal pyramid. Notice those are not the same. Tetrahedral and trigonal pyramid are not the same. Let's do another example. Here's water. Water, if you look at the central oxygen atom, has, if we count up electron groups, here's a single bond, another single bond, and then 2 lone pairs. That's a total of 4 electron groups around the central oxygen. Tetrahedral electron geometry. Of the 4 electron groups around the central oxygen, 2 of them participate in bonding. So 2 of them are forming a bond to a hydrogen atom. The other 2 are not participating in bonding. They are lone pairs of electrons. So if you mentally subtract out the lone pairs, what you're left with is a molecule that looks a bit like a boomerang. Okay, boomerang. Let's give that a name. The electron geometry is indeed tetrahedral, but we call the molecular structure or molecular shape bent. Bent is the name, or V-shape. Some people call it V-shape, but the idea is it's simply a bent molecule. It's like a boomerang. All right. So students, if molecular shape is not the same as electron geometry in all cases, in fact, probably more frequently than not, they're different. Let's make a little chart here. And this is a chart that you'll be able to use on tests and quizzes coming up. So if we're counting up the number of, in this chart, they say number of electron dense areas. That's another way of saying electron groups. Okay. Electron pair geometry, that's the same as electron geometry. And then we're going to go through what happens if there are no lone pairs of electrons, 1 lone pair of electrons, 2, 3, or 4 lone pairs. If there are 2 electron groups, your electron geometry is called linear. And students, there's no way for a lone pair of electrons to exist if there's only 2 electron groups. So the molecule will necessarily be linear in shape if you have 2 electron groups. Notice, if there's no lone pairs, the electron geometry name matches the molecular shape name. What if there's 3 electron groups? We give a name for that of trigonal planar electron geometry. Of the 3 electron groups, if there are no lone pairs, they're all participating in bonding, then it's also called trigonal planar molecular shape. If there's 1 lone pair, so picture this gray dot is the lone pair, then the molecular shape that's left is bent. How about 4? If there's 4 electron groups, we call the name of the electron geometry tetrahedral. And if there's no lone pairs, like we saw with the CF2Cl2, then you have tetrahedral molecular shape as well. But what if it's like ammonia, where it's tetrahedral electron geometry, but there's 1 lone pair? Then we have a trigonal pyramid molecular shape. Or what if it's like water, where there's 2 lone pairs? 2 lone pairs of electrons gives us a bent shape. And then things can get wild here. This is kind of the fun part of chemistry. If there's 5 electron groups, the name of the electron geometry is trigonal bipyramidal. If all 5 electron groups are bonding groups, then it's a trigonal bipyramidal molecule. But what if there's 1 lone pair? We call that sawhorse or seesaw. Some textbooks will say seesaw. What if there's 2 lone pairs? They call that a T-shape, because subtracting out the lone pairs, you're left with a molecule that looks like the letter T. Or what if there's 3 lone pairs? Then you're left with a linear molecular shape. All right. What if we're talking about 6 electron groups? The name for the electron geometry is octahedral. If all 6 electron groups are bonding groups, then you have octahedral molecular shape. If there's 1 lone pair, we call it a square pyramidal molecular shape. 2 lone pairs, square planar. 3 lone pairs, T-shaped. Again, isn't it funny how when trig bipyramidal electron geometry has 2 lone pairs, you get T-shaped, and when it's octahedral geometry, if you have 3 lone pairs, you get the same T-shaped molecule? It's kind of cool in a chemistry sense, you know? What if there's 4 lone pairs of electrons? Then we would have a linear molecule. Molecular shape linear, just like we saw molecular shape linear in trig bipyramidal electron geometry with 3 lone pairs. And we saw with 2 electron groups in linear electron geometry. Students, this chart is very helpful, and I'm not going to ask you to memorize it. I'll give it to you on tests and quizzes. Okay? All right. One last little bit. I know there's been a lot here. Let's try a comprehensive question. Let's say that you and a team of chemists have been able to isolate and identify a compound called phosphorus trifluoride. And it's a compound that could potentially help your research. But to determine whether indeed it will be helpful, you've got to predict its molecular shape. Okay. We're just given a name of a compound here, students. The problem is asking us to arrive at a molecular shape. So to get there, number 1, convert a name into a formula. Oh my goodness, do you remember this? Nomenclature. 2, draw a good Lewis structure for phosphorus trifluoride. 3, determine electron geometry. There's going to be a central atom there. Count the number of electron groups around the central atom. And based on that, name the electron geometry and the bond angles found. And then 4, determine molecular shape based on the number of lone pairs of electrons that are found. Go ahead and pause the video now and try this problem before we go on to the answer key. Okay, first things first. You're given the name phosphorus trifluoride, and you know chemical nomenclature. Now, conveniently, this is probably the easiest type of compound to decode. If there's a prefix, tri, that means there's 3 fluorine atoms. And if there's no prefix in front of phosphorus, there's just going to be 1 phosphorus. So it's PF3. Next task. Draw the Lewis structure for PF3. Now, you know how to do this, students. Begin with dot diagrams for each atom. So we've got 1 phosphorus and 3 fluorines. Here's phosphorus, group 15, right below nitrogen. 5 dots, because there's 5 valent electrons for the atoms in that column. Fluorine, group 17. Every atom in group 17 has 7 valence electrons. So each of the fluorine dot diagrams will have 7 dots around it. Okay, let's add together the number of dots for each dot diagram. 5 plus 7 plus 7 plus 7, that gives us 26. So mentally I'm thinking 3 times 7, that's 21, plus 5, that's 26. 26 total valence electrons. Next, the central atom is going to be the one that you only have 1 atom of. So if there's 1 phosphorus and 3 fluorines, phosphorus will be the central atom. Let's first connect the central phosphorus to the satellite fluorine atoms with just single bonds. Each of those single bonds consumes 2 electrons. So we're going to subtract 2 times the number of single bonds from the total number of valence electrons. So we form 3 single bonds. That uses up 6 of the 26 total valence electrons. So 26 total valence electrons minus the 6 used to make single bonds in our initial structure. gives us 20 electrons remaining. Our goal is to satisfy octet rule if we can with the 20 remaining electrons. And if you divide that up so as to put 6 dots around each of the fluorine, that uses up 18 electrons, and then the remaining 2 dots around the central phosphorus, then you've successfully satisfied the octet rule for all of the atoms in this Lewis structure. Good job. This is a beautiful Lewis structure. Now, you might say to yourself, gee whiz, I remember that sometimes it's possible to violate the octet rule. And you're absolutely right that in this compound, phosphorus would be eligible to violate the octet rule. It is the central atom, and it's not in the first 2 periods on the periodic table. But as a general rule of thumb, and I guess I would say as a general rule in life, don't break rules unless you need to. Sometimes you've got to break rules, and when you do, okay, go for it. But when you don't need to break rules, don't do it if you don't have to. Okay, back to chemistry. We're going to determine the electron geometry by counting the number of electron groups around the central phosphorus. So if we go to our beautiful Lewis structure and focus in on the central phosphorus, I see single bond number 1, single bond number 2, single bond number 3, and then a lone pair of electrons. Each of those counts as 1 electron group. So that's a total of 4. The 3 single bonds and the lone pair all count as 1 electron group, giving us a total of 4, which of course gives us tetrahedral electron geometry. Bond angles in any tetrahedral electron geometry arrangement is 109.5 degrees. Now for the last piece. We've written a good Lewis structure. We've named the electron geometry. Now we've got to figure out the molecular shape. Here's your Lewis structure. Consider this chart. When you have 4 electron groups, that's tetrahedral electron geometry. If there were no lone pairs, I would also say that the molecular shape is tetrahedral. But we don't have no lone pairs. There is 1 lone pair here, 3 bonding pairs and 1 lone pair. So on the chart, we're looking in this column where it says 1 lone pair. That gives us trigonal, pyramidal, or trigonal pyramid, if you prefer, molecular shape. And that's all you need to do for the assignment.